easier than doing an email, but yeah, just since I did send one out this morning, figured probably should figure that out. Is that actually working? Am I just screaming into the void? Do a bit of both, you know. Give people a few more minutes. One thing as folks sign on, say slowly in case because I can't see everyone who's here. If while you were listening to Jesse's talk, you were like, I'm interested in grad school. Jesse seems really cool. I wonder if I should be applying to Vanderbilt. One thing she did mention is that although she does not currently have much space and or funding in her group for another grad student, there are other professors at Vanderbilt looking for grad students. There was one she specifically mentioned, I'm forgetting his name, but does gravity wave research. So if that is something you are interested in, she would be very excited to set up a Whitman to Vanderbilt pipeline as well as the Wyoming and New Mexico ones that already exist. So if you are in that part of your career where you're thinking about grad school, Vanderbilt might be a good option. She's also more than happy to talk to anyone. I put her email information in the assignment for the AGN speaker assignment. So if you want to get in touch with her, she is very happy to talk to Whitman students. So know that she's an awesome resource, both for learning cool things about AGN, but also just for being a great resource for Whitman students, building our network of astronomers from Whitman. Looks like we have a pretty good quorum, so I'm going to slowly get started on kind of what we're going to do today, but also talk a little bit about, you can see there's a lot of tabs open, which I guess you can see that are kind of just some different things I want to highlight as we start moving towards the end of the semester. Kind of crazy how it's coming up. So today we're going to talk about IFU surveys, which are a little bit of a new form of extragalactic astronomy that I think are really kind of cutting edge and the future. One of my goals for this course is to give you the tools and knowledge so you could go into any talk on extragalactic astronomy and kind of understand what the people are talking about. And at one of the conferences I went to recently, it was like 1 out of every 3 talks was about IFU surveys. So I think understanding, there was a reason for that. It was in Sydney, and one of the surveys you'll see is very Sydney based. So that was part of the reason for it. But it is a big topic of conversation in extragalactic astronomy, so I wanted to make sure we talked about them, and there's some fun stuff we can do with it. But before we dive into that, like I said, I wanted to just very briefly hit on kind of where we are in our semester. So we've done all of these days, all of September, all of October. We're here. There's 2 more weeks of y'all listening to me, and then there's going to be 1.5 weeks of y'all listening to each other. So just to kind of show, next week we'll be kind of starting the week by doing something that I hope will be kind of fun, where we'll, not that I thought any of this was terrible, but I think this will be fun too, where we're kind of going to bring in a lot of the information we've built over this semester to think about how we can use different parts of the electromagnetic spectrum to study galaxies. So the 2 readings for next class, they're both pop science articles, so they're pretty easy to read. And I'm going to really encourage you to read them, because the last thing we'll do on Tuesday will be kind of debate over which of the decadal telescopes should be the next space telescope after James Webb. So having a little bit of a background information for that, I haven't been quizzing you about the readings. These will be 2 readings that will be pretty short and painless, and will help you prepare for our activity at the end of Tuesday. Then we'll talk about, on Thursday, we'll talk about some of the outlier galaxies that I think are fun. So that'll just be kind of a cool, like, here's all the weird stuff that's in our universe that doesn't fit into any of the boxes that I have defined so far. And then we'll think about how we can use those to maybe study universal evolution and other things. And then the last week of me talking at you will be focused on first the galaxies in our local volume and what we can learn from studying the nearby galaxies, and then also what structure looks like in the universe. And we'll get to play. It says fire. I've decided that we're going to use illustrious instead, but the main thing is we're going to be playing with cosmological models of the universe and thinking about how those are made. So that's kind of my plan for the next 2 weeks. After that, I have scheduled time for student presentations. So that will be the last 3 weeks. I need to get a sign-up sheet up probably tomorrow for you to sign up for times. There's a lot of information about your final project in this final project assignment. It should look really similar. If you've been in a 300 level class, I think they all have final projects where you do a kind of medium-ish paper and give a presentation. Same-ish kind of thing, 10-ish minute presentation, 4 to 7 page paper, with the goal being for you to practice reading academic papers and then presenting astronomy to astronomers. So that's something that you do in grad school, is write papers and review research papers and then also present. So this is kind of practice for that, and also practice for just going into the field of astronomy in general. These are all good skills to have. I will say, just as a kind of note, in case you weren't excited enough to listen to your peers talk, you will be getting attendance points for this, and there will be 2 questions on your final that will be based on what people share in their final projects. So more reasons to attend. There's a little bit, I think this is pretty much the same information that is here, but then in this PDF, there's also some rubrics that kind of have how I will be grading your paper and presentation. Maybe some things that are slightly different. I do want you to have an abstract. So that's just a little short, like 1 paragraph summary at the beginning that tells me what's going to be in the paper, because that's something, again, that you'll need to do if you go into astronomy. So not something to stress about, but I do want to see an abstract. Otherwise, again, probably nothing crazy here. And then presentation, mostly we're gonna have to time this really nicely, so please don't go outside of the time limit. And then just kind of, is it clear? Is it understandable? And then are you using good slide etiquette where I'm not just seeing a jumble of text in every slide? Other notes on this, I am not going to give you a list of topics. I'm not going to assign you topics because I would rather you pick something that is exciting to you and not let me put boxes around you. So it's open, with the caveat that if you do not have an idea, come talk to me about stuff that excited you and we can find a good topic for you. So if you don't have an idea, fine, talk to me. If you do have an idea, awesome. Maybe shoot me an email and say what it is, but it's probably fine because I want it to be something that's fun for you to research, and not, me telling you what to do. So if you don't have an idea yet, maybe there was something from Jesse's talk that you would like to learn more about the last parsec problem and research that. Maybe when we talk about weird galaxies, you're like, hot dogs sound really cool. I want to learn more about hot dogs, which is a type of galaxy. So I promise I tried to get enough food-themed galaxies in there. So maybe that's something that stood out and you want to learn more about those, but just something to be thinking about as we kind of move towards these presentations. The papers will be due kind of on the final, so you don't have to turn in your paper with your presentation. You can, it's up to you. We will also have a final exam on our final exam time, sort of, that will be based, it won't be cumulative, it'll be based on this kind of second half. So that's kind of the end of this semester. Our Spectra project is due in not too crazy long. Again, I updated that a little bit. So if you're having too many Seagal problems, there's an alternative where you can pick one of these papers. I don't know if I already have that open, and give me a little, just read one of these and give me a little bit of a summary. So these are all papers that use Seagal to do some sort of analysis of galaxies or of a galaxy. And so just picking one that sounds semi-interesting and reading through it and giving me a little summary that kind of translates from science talk to normal human English. So that's the idea of an alternative if Seagal is causing you too much problems. I've talked to a few people who seem to have gotten it running, so it's possible, but it is kind of a mess, and it's difficult, but it's a good thing to learning to download and get programs running is another thing that you will do. Whether or not it will be Seagal, there will be something that you'll have to download and get to run. So it's a good thing to practice, but just don't bang your head about it for too long. The second part everyone will do, sorry, Erin.
I think you were about to answer my question, so you can keep going.
Okay. So part 2, where you're doing line fitting, that whatever you did for part 1 for the Seagal fitting, everyone will do that line fitting. So that, I think everyone was able to, or most people have turned in their BPT diagram thing. So it's just repeating that, but for data for your galaxy, with a little summary of which line you chose and why. But I think that should be less of a problem since you all have Anaconda, and that'll just be working with a text file. So it shouldn't be too terrible. That was a lot of stuff about what's happening soon. Any questions? Cool. Oh, one other thing, sorry. I meant to say this and I wanted to show you this. I say this in the final project thing too. I am not going to require you to use LaTeX. I highly encourage it because it's a good skill to have. It's a good thing to practice. If you have not used Overleaf before, Overleaf is a really nice way of writing in LaTeX. So it's just kind of a word processor where you can create projects and it uses LaTeX to do it. So this was a paper that I'm currently working on in Overleaf. It's a free thing, you don't have to pay for anything, and you can type in LaTeX and cite papers easily and fight with figure placement for too long, or whatever else. So again, not required that you do it in LaTeX. If you do, this is a useful tool. I highly recommend getting this practice, but again, not going to require that. That was it. Now we can talk about IFU surveys, and I can nerd out over how cool they are. Okay, so IFU surveys are integral field unit surveys. Sometimes you'll also see them called IFS surveys. So IFU or IFS, it's the same thing. And they're surveys of galaxies. So a survey is just where you image a lot of the sky with one telescope, one instrument. An integral field unit is when you get a data cube for your galaxy. So, or whatever else you're looking at, I should say. So they're made using kind of these fiber optic hexabundles where instead of just getting one image, you're getting a spectra for every pixel in your image. So there are spectroscopic surveys where you just kind of do spectral slits on a bunch of galaxies, or narrowband imaging. There's photometric surveys where you get photometry for all of the sky. And now there are these new IFU surveys where you're getting spectral cubes, data cubes, where for each galaxy or other thing you are imaging. So they're just this really neat kind of combination of photometry and spectroscopy, because we're kind of getting a two-dimensional picture with a third dimension of spectral information. My advisor likes to say there's actually 4 dimensions. So there's 2 spatial dimensions, X and Y. We can't go into our galaxy. We can't get a third dimension. It's there, we can't do it. It's too far away. But instead we get a wavelength dimension, so we can see the galaxy at different slices of wavelength. And then there's an intensity dimension. So every pixel has a position in space, a wavelength that it's imaging, and then it has a brightness. So you can think of that intensity or brightness as a 4th dimension for these images. So the actual optics of how this works, it's a little bit more complicated than I completely understand and want to dig into. Today I'm going to more focus on the science we can do once you have your survey data. So maybe if you want to dig into the optics, that could be a project. It would be gross, in my opinion, because digging into optical physics is a lot of tricky geometry that I don't want to do. But the main thing is that they use these fiber optic hexabundles where you're kind of taking photometric data and you're getting spectral information for every pixel position in your image. You guys have already worked with one data cube, but I just think data cubes are magical in so many ways, and I want to highlight how cool they are again. So when you guys found the rotation of NGC 7331, that was working with a data cube where we had spectral information specifically for the 21 centimeter line. So that was just kind of a data cube centered on the 21 centimeter line, where we had an X and a Y and then a spatial or a spectral dimension as well. So we could kind of slice through at different wavelengths. These IFU surveys, same kind of thing, except now instead of being centered around one line, we're looking at typically the entire optical spectra. So these are mostly focused on optical light, visual light, visible light, sorry. But that's not just centered on a line, but getting the entire spectra and getting that as a function of position, which is just very, very neat. There are also some telescopes that do this in the infrared. So you're not limited to optical. I don't think there are any UV, but there are some that look in the infrared. So you can do like surveys of the PAH features as a function of position, which again, cool. But we're gonna focus on some optical ones. There's quite a bit we can learn from IFU surveys. It kind of depends on what you want to look at. I guess I should pause there first. Are there questions about data cubes and just what they are? Besides amazing. Okay. So we can learn a lot from IFU surveys. For example, I'm not going to focus on globular clusters because this is galaxies, but if you did do an IFU survey of globular clusters, you could get the spectra of all of the stars in that shot and make kind of an HR diagram for your globular cluster with also metallicity information and all this other stuff, which would be useful if you wanted to find the age of your globular cluster. So they're cool for that as well, but we're going to focus on galaxies because this is galaxies class. And galaxies are cooler than globular clusters, which you should all definitely tell Nathaniel I said is a fact. It's just true though. They're prettier, they have dark matter, they're just awesome. But when we're looking at galaxies with IFU surveys, anything that's an extended object, you get spatially resolved spectra for these extended objects. So galaxies, nebula, and then also spatially resolved velocity information, which can tell us about rotation. It can tell us about velocity distribution, so how organized is the rotation, just all other kinds of things like that. And then they're a neat way to kind of optimize your telescope time. So instead of having to do a lot of spectra to cover one galaxy, you're just doing them all at once. So you're getting it's like taking hundreds of spectra slits and getting the entire galaxy. So you're optimizing your telescope time at the same time. So we're going to dig into a lot of those really quickly, just what I mean and examples of how those are being used. So the first thing I said is that we can get velocity information. So the idea is, again, kind of similar to what you guys did when you measured rotation. You're looking at the shift in a wavelength peak of an emission feature in every pixel to see how that pixel is moving with respect to all the others. So we can see rotations of the galaxy, we can see perturbations in that rotation that might be caused from a bar, even if the galaxy is not tilted in a way where we can observe a bar, or if it's fuzzy enough that we couldn't see a bar without data from a space telescope, you might still be able to tell if there's a bar there based on velocity structures. So we look at different pixels, look for peaks in the emission line and see how they're shifted in different locations to get an idea of the velocity structure of the objects included in IFU surveys. Another kind of neat thing, which I'll show you later, is that you're not just getting the velocity, you can get the velocity of different components of your galaxy. So by looking at the shift in H alpha, that might tell you about the hydrogen gas, whereas looking at the shift in other emission features might tell you more about the stars. So you can compare the velocity of the gas to the velocity of the stars by looking at the shifts in different emission features. And then do this for a buttload of galaxies because this is a survey. So there's hundreds to thousands of galaxies depending on what survey you're looking at. So as just kind of an example of thinking of this kinematic observations of a galaxy, this is from the manga survey, which is the one that we're going to work with today, where we have this observed galaxy. Let me get my pointer here. So it just looks kind of boring if you just looked at like the SDSS image of it, but they can get the velocity structure for all of the different parts of this galaxy. So we can see this side is blue shifted, so this side is rotating towards us. This side is rotating away from us. We can also get the velocity distribution. So it looks like the center, the bulge of this galaxy has more random motion, a larger velocity distribution, whereas the edges of this galaxy are more organized, all rotating together with this rotational motion. So kind of what you would expect. And then they can also compare that to models to try to get ideas of what the dark matter halo might look like for this galaxy. So they have two models here that they're using. The thing is, these IFU surveys, one of their limits is they're typically fairly small areas on the sky, which I will talk about more. So they're measuring a dark matter halo. You usually kind of want to get more of the extended disk, which we're not getting in this survey. So that's slightly problematic, but and it makes it hard to compare their model with no dark matter and their model with dark matter look pretty similar. And the only thing they're changing here is how they set up their initial mass function. So whether it's a initial mass function with a heavy initial mass function, so there's bottom heavy initial mass function where there's a lot of dwarf stars, but that aren't maybe putting out a lot of light, or a light initial mass function. So bottom light, there's not a lot of low mass stars that aren't putting out a lot of light. So this is more stellar mass, no dark matter, less stellar mass, yes, dark matter, produce about the same thing. But this is a IFU survey, so we have even more information. We can break this degeneracy by looking at the different emission lines and using those to determine what sort of stars are there. So that's cool too. But the main thing I wanted to point out is just this really awesome velocity maps that they can make using IFU surveys. So that's the first thing we can get, is these kinematic structures, this velocity information that we can do by looking at the shifts in the peak wavelengths. Any questions so far? So we also get spatially resolved spectral line information. So we looked at how we can learn things about galaxies based on the strengths of different spectral lines. We mostly talked about doing that kind of just, when I was talking about it, I was thinking about doing it for like the whole galaxy or one star forming region. But now we can do it as a function of position if we use these IFU surveys, which again, super cool. So this is an example here where they're showing the H alpha emission for two different galaxies that look pretty similar if you're just looking at these optical images. But when you look at the H alpha, we see that one of them has a ton more H alpha light. So this one goes up to 1, this one goes up to 0.5. So even the brightest parts of this image are only, I guess, like the faintest parts of this image. So the scales are not matched, which is frustrating. Don't do that if you're publishing papers. I think it's bad. Although I am doing it in a paper, so depends on what you're doing. But the point is, this one has a lot more H alpha light, which tells us there's a lot more young stars in this galaxy, where this galaxy is quenched, it has no H alpha light, and we can see that there's some star formation happening in this side over here for some reason, but there's pretty much no star formation in this galaxy. It's very low in that H alpha light. We also see spatially resolved information, so there's more star formation happening right around the bulge of this galaxy and less happening in the disk at this moment, so that's kind of cool. They also compare it, this is another spectral feature, so this is a dip. So I think that's the D around 4,000 angstroms, sorry, D4000. This is this dip around 4,000 angstroms, which they're using as a proxy for the age of the stars. And so what we can see is that the quenched galaxy has more old stars, whereas the unquenched galaxy has more young stars, so kind of what you would expect. But even though they look fairly similar just in the image, we can now say that this is probably a spiral disk galaxy that's more face-on, whereas this is probably an elliptical galaxy, and that has stopped forming stars, where this one is continuing to form stars. Besides just looking at H-alpha, you can also get spatially resolved BPT diagrams and see how like the kinematic structures might influence star formation rate and other stellar properties. So just really neat what we can do with these kind of things. So another example, like I said, you could do a resolved BPT diagram. So we made a BPT diagram for NGC 6946, but we were pretty much just looking at the entire galaxy. This is now looking spatially resolved version of this. Again, just kind of issue with IFU surveys is they're usually not wide field of view. So they're not getting the whole galaxy in this image, it's just this hexagon here. But what we can see is I think red is more of that AGN dominated, blue is more star formation dominated. And you can start to see that the center of this galaxy, the most highly ionized gas is probably dominated by a central AGN, even if in the disk of this galaxy, it's more driven by star formation. So if we only did one BPT diagram for this galaxy, we might see what's happening in the disk, but not what's happening in the center, where an AGN is driving the ionizing radiation, which might be an issue if then you wanted to study a star-forming galaxy and you put an aperture down only around the center. So important to have this kind of information, and just cool that we can now see how different parts of the galaxy are showing these different line ratios and getting this spatially resolved information, so not just one measurement for a galaxy, seeing that it is probably a function of where you are within the galaxy. I might be over here jumping around being super excited, but IFU surveys have some pretty big limitations at this point. So the first one is that they're really only good for very nearby galaxies because you need bright sources that are going to be spatially extended. So when we start looking at redshift of 1 or 2, they're going to look kind of more like points, like we saw with the Hubble Deep Field. There was a little bit of a spatial extent, but they were more kind of almost point sources. So the deepest these surveys will look is about a redshift of 0.2. So you're limited. It's still really helpful to get this data, but you're going to be limited in space. They're also not going to be super high resolution. So we can kind of see that here. This is the PSF for this image, so the point spread function. When you guys measured your point spread function, any structures you see that are smaller than this circle are kind of suspect. So the point spread functions are going to be, you're getting spatially resolved spectral data, but it's only so good. So that's, if you want really high resolution data, you're going to use, a larger telescope or a space telescope or something. Larger is the more important thing. So angular resolution depends on the diameter of your mirror. Usually these IFU surveys are not on very large telescopes, usually around 3-meter telescope class kind of thing, 3 to 4. So not huge. And then this resolution is also going to be determined by the size of your pixels, which are called spaxels or voxels, depending on who you talk to. So when you're working with a cube, you get these spectral pixels or spatial pixels, which are called spaxels. Some people also call them voxels. As far as I can tell, those are the same thing. I have not, every definition I see, it's like, yeah, that's the same. So I can't figure out if there's a difference. I haven't figured it out. But you're limited in resolution by the size of your pixels. You're also limited by low surface brightness. So to get spectra, you either need really faint things, you either need a really, really long observing time, or you need a bright source. So with a survey, they're not doing really, really, really long observations. They're just getting the bright data. So anything that's low surface brightness, they're going to miss. And also if you want to see the edges of a galaxy, you're going to miss it too, because they're usually not wide field of view kind of things. So you're limited by the size of your hexabundle and also by brightness. So we're not getting the outer edges of this galaxy here, what we can see. And so the reason why this image is here, this is another, I guess I'm kind of talking about my advisor a lot today for some reason. But this is one of the things from his paper, so I know it a little bit better, where he is not working with an IFU survey. He wants to find, he's working with photometry of these galaxies and looking at the ages of the stars in these galaxies as a function of radius. And an IFU survey would not be able to do this. It would not be able to get information out here, kind of these outer rings. It would miss that. So what he does is he plots the age or the color of these galaxies, which has to do with the age. Bluer is younger, redder is older, as a function of radius. And I'm pretty sure that, like, I'm not sure exactly, but I think most IFU surveys would end somewhere around this 1. It depends on the galaxy you're looking at, how far away it is, because this is like, I think this is like the quarter light radius. So it depends on where you're looking. But you can't get these kind of tails that are what my advisor is really interested in. You're going to be limited to the bright centers of galaxies. So they're really, really cool, but like every part of astronomy, there's going to be limits to what you can do with them. So, yeah. Okay. So that is kind of my overview, broad overview of IFU surveys. I'm now going to talk about 3 IFU surveys in particular, and then let you guys play with some IFU survey data. Before we jump into SAMI, any questions, anything still confusing? Okay. So I think I might have mentioned SAMI very briefly. This is the one done in Sydney. So this is the Sydney, let me get this right. How they made this into SAMI is kind of a mystery. So it's the Sydney Australian Astronomical Observatory Multi-Object Integral Field Spectrograph, or the SAMI survey. So their SAM and I are in that. There's a lot of other letters too. But that's okay. That's how we do it in astronomy. You just kind of do whatever you want. And their main goal for this survey is to try to figure out the role of the environment in galaxy evolution. So how galaxies are forming stars over time and how the gas and the stars in a galaxy are comparable. So this is kind of their big poster that they always show. So this is all of the galaxies they looked at, where we have the mass, the dynamical mass. So this is the mass that you would determine using the laws of gravity, so the total mass of the galaxy, versus the metallicity. So here 0 would be solar, negative is less than solar. We can see there's kind of this trend. Lower mass galaxies have lower metallicity. Also, they're going down to slightly larger than dwarfs. So dwarfs are kind of 10 to the 9 and smaller. So these are mostly normal galaxies with maybe a few edge dwarf-y type things. And for each galaxy they look at, they make these different maps. So this is one of their maps where we have, this is the Hubble data, what it would look like with Hubble. This is their kind of UGRIS, SAMI UGRIS data. So you can kind of compare the resolution. Hubble does better, which is what we would expect. So you can compare the resolution between those two to get an idea of SAMI's resolution. Down here, this is the H alpha data for this galaxy, so the spatially resolved H alpha intensity. And then on either side, they have the velocity for gas and velocity for stars. So gas velocity, star velocity, gas velocity distribution, star velocity distribution. So a lot of the work being done with SAMI is kind of comparing the velocity distributions in the stars and the gas. Again, this is the name, the Sydney Austro-Anglo Observatory Multi-Object Integral Field Unit, so SAMI, somewhere in there. It's on a 3.9 meter telescope somewhere in Australia. And it's covering a range of about 300 to 900 nanometers in wavelength, so again, kind of focused on this optical part of the spectrum. This is just a little bit kind of nitty gritty about the optics again. So there's 13 fiber-based IFU hexabundles, each with a 1.6 arcsecond diameter, giving it a 15 arcsecond field of view. So that's one of those limits, is pretty small field of view. 15 arcseconds is not huge. And they have so far imaged 1,559 galaxies. So they have a pretty big database, all of which they have this kind of nice data sets ready to go. So one of the things, like I said, that is being done with the SAMI survey is comparing the motion of the gas in a galaxy to the motion of the stars in a galaxy. So this is from a paper, Bryant 2018, where they looked for galaxies that had the gas and the stars not rotating together. So this column here is showing the rotation they measured looking at the H alpha line, so the gas rotation. I'm not exactly sure which line they used for stellar velocity, but they can measure the stellar velocity as well, probably with some sort of sodium line that we would expect to see in the outer layers of stars. I'm not sure, sorry, I should have looked that up. But what we see is that they're not always nicely aligned. So the rotation in the stars and the rotation in the gas are very often misaligned. And that might tell us something about how the galaxy is accreting gas and how long it takes for, after we accrete our gas onto our galaxy, how long it takes to turn that gas into stars. So if we were accreting gas and immediately turning it into stars, we would expect the gas and the stars to be nicely aligned, all orbiting together. That is not what we always see, which might suggest that it takes a while, gas gets accreted on, slowly starts rotating together, and eventually starts forming into stars as it collides with other gas clouds and starts to orbit on this different path, this stellar velocity path. And just to show that, so this is kind of like just me geeking out over cool results from IFU surveys, but they plotted different galaxy types and looked at how aligned or misaligned the gas was. And what they found was that if you have really misaligned rotation between your gas and your stars, you're going to be kind of an early type galaxy, so an elliptical, maybe an early type spiral. So these are our SA spirals, whereas this is going to be SC spirals over here. So most of our spirals seem to have pretty good alignment, but if you look at the kind of funky rotation that you might measure in an elliptical, whatever slight organized motion you can get, it's not necessarily going to be aligned between the gas and the stars. But it's not really a function of stellar mass, which is also interesting. So cool data that you can get when you're working with IFU surveys, and you can measure the rotation of individual components because you just have a ton of galaxies because you have this spatially resolved spectral data. So the second survey, and this was the one that I think you're reading, was a paper about CALIFA. So CALIFA is the Caller Alto Legacy Integral Field Area Survey. So at least CALIFA, they got all of their letters in and didn't add too many extra. This one is looking at slightly larger field of view than some of the other IFU surveys, but because of that, they've gotten fewer galaxies. So they have to observe for longer. So they've looked at 667 galaxies instead of over 1,000 Still a bunch though. And they're working with a 3.5 meter telescope in Chile, I believe, trying to get, let me get my notes here. So their main goals for this are to determine extended kinematic classifications across the entire Hubble sequence, look at the ISM in different galaxies, study how AGN and star formation shocks heat gas, study stellar populations in the outskirts of disks to understand radial migration and star formation, so stars moving in and outside of the disk. And it just, a lot of really nice data. So this is kind of their big poster that gets thrown around where you can see kind of an image of what a hexabundle might look like. So this would be one galaxy, each hexabundle getting spectral information for each position. And then these are just a bunch of their galaxies. So I don't think there's actually all 600 of them, but looking at different data, again, kind of similar where images and then velocities and line fluxes and other cool things. So the project they had highlighted on their webpage is the one I pulled in for this, and this was a result from Perez in 2013 that looked for evidence for inside-out galaxy formation. So this is the idea. Inside-out means that we form the stars in the center of our galaxy, and then we form the stars in the outside of our galaxy. So bulge forms first, has more old stars. Disk forms later, has more young stars. So that's inside-out. We form inside first, outside later. As opposed to outside in, where we would form outside first, inside later. There are arguments for both, but this is an argument for inside out. So the way they did this is because they have spectral information for every position in their galaxies, they can use SED fitting kind of techniques to get a star formation history for each pixel, to get the ages of stars at different radii. So we can see, are there more old stars in the center or are there more old stars in the disk? And what they found, we're going to focus on these solid lines because they make more sense to me, is that if you look in the inner part of the disk, so this black solid line, there's a larger fraction of old stars. So this is the fraction of the stars that are a certain age. So 8 billion years or not 8 billion, sorry, 10 to the 8th years old or 10 to the 10th years old, so log age. So 10 to the 10 years, 10 to the 8. And we can see that in the inside, there's a larger fraction of stars that are these older stars, whereas you move out, so 1/2 light radius, this pink line, more of the stars are younger. So there's fewer, there's less of a fraction of the stars are 10 to the 10. It's like 40% of the stars are older than 10 to the 10 years old, which is an argument that, yeah, it seems like for the most part, the center galaxy forms first. There's a little bit of a flipping around when we get to this really outer edge, so above the half-light radius, where you can kind of see it has more older stars, which is maybe an argument that when you start getting far enough out, there is some outside-in formation as well. It's overly complicated, and we don't need to get into that in this class. But this is just, again, a cool thing where we can get stellar populations as a function of position in a galaxy, which allows us to kind of get an idea of the evolutionary history of a single galaxy, which is neat, instead of having to just compare a bunch of different ones at different times. So the last one that I want to focus on, and this is the one that y'all are going to play with, is MANGA. MANGA is the Mapping Nearby Galaxies at APO. APO is the Apache Peak Observatory and is also where SDSS is, so where the Sloan telescope is. So this guy up here, so this is Sloan's version of an IFU survey. Again, looking at the visual, slightly smaller field of view than Khalifa, but they've gotten tons and tons and tons of data. So they've gotten over 10,000 nearby galaxies with this IFU thing. So just a huge sample set of nearby galaxies. with a limited spatial resolution, they're looking at near enough stuff that you're getting spatial resolutions of 1 to 2 kiloparsecs. So angular resolution transforms to a spatial resolution. Nearer galaxies, we get better spatial resolution. Further galaxies, you get closer to the 2 kiloparsec. But it's still really good. So getting pretty good resolution data despite the fact we're an IFU survey, or they are an IFU survey. And it's another one that is mostly focused in the optical part of the spectrum. The really nice thing about Manga is that they have a nice user-friendly website where you can play with their data, and it is called Marvin. Marvin doesn't stand for anything. It is literally just named after the robot from A Hitchhiker's Guide to the Galaxy. So you get to throw in depressing Marvin in quotes when you talk about this. And that's what we are going to work with. So we're going to play around with Marvin, hopefully be slightly less depressed than he is as we do it. And that's going to be our main goal for today. So in your assignments, let me see if I can find it. Make sure I know what it's called. Aha, it's called Marvin and IFU Surveys. And then there's this quiz that should be published and viewable. This is our first thing where we're going to play with online data, where if you have good Wi-Fi, it might be really nice for you to share your screen with your group because some of this is going to take a little while to load. So I'll say that. This is not as bad as the illustrious simulation one is going to be, but some of it will take a little while. So this might be a group effort. But if you click on this link, it'll take you to the Marvin page where you can work with Marvin and the Sloan telescope. I've given you a few plate IDs to look at. So the way you do that, you just copy this and stick it right here and then go to it. And it'll give you the plate. In order to play with the spectra, you have to turn this on. It takes a second to load. But then this also takes a second once you figure it out. But you should be able to click around and get the spectra for different parts of this galaxy, which is cool. So I've asked you a few questions based on playing with that. And then there's also, they've made some nice maps. So this is like the stellar velocity map, so we can see how the stars are rotating. I've asked you a few questions about those. I don't think you need to, but if you do, you can load other maps as well from here. Just make sure after you choose your map, you hit get maps so you can load them. So if you wanted this one, you would have to hit get maps afterwards, and then it would load it. The nice thing is it doesn't remove the ones you already had, so we just now have a new get map as well, showing the data for the neon 3 line that I just loaded here. So I have asked a few questions to think about what we can learn from these. There's also a second one, same kind of process, just input a new plate ID and it'll get you to this new galaxy so you can compare a couple. But I just think it's really fun and neat to play with. So that's going to be what we do for the next little bit, and then we'll come together at the end of class to discuss what we found very briefly. As I open breakout rooms, if anyone has questions, shout them out. Otherwise, we will go for it. Ethan, did you have a question?
Yeah, I was going to ask, do you want us to turn in like one singular thing for each group? Because you said you wanted to share screens, or should we all like write one individually?
So this would be, I still kind of want you guys to rate each one individually. It just might be if there's someone in your team who is having a really hard time getting data to load, it might be nice to work a little bit more collaboratively. So yeah, good question. I will be around to bug you as you work with this, and also to answer questions. Always feel free to grab me. And maybe we'll aim for about 20 minutes with this, and then 10 minutes for discussion together. So Rooms should be open.